Hello, everyone. Welcome to Haskell 101. My name is Antoine. I'm a cloud big table SRE in Dublin, and I use they, them pronouns. Welcome. So you're trapped in this room for 3 hours with me. So what's the point of today? Well, Haskell is known to have a steep learning curve. So a lot of people have tried to learn the language on their own, and you might have realized that there's a lot to cover before you are able to write your own first hello world. So the point of this 101 is to help you get started. As in, I'm going to try to cover all the things you need to know in order to be able to write your own programs. So the way this is structured, I have roughly an hour of slides and an hour and a half of exercises, the code lab I asked you to download before the session. The point is to make you write code, because that's the only way to make any progress. There is quite a lot of you today, but please do ask questions. Please do interrupt me. Please do ask questions. The best sessions are the ones in which a lot of people ask questions, because I can talk about more things than what is covered by the lesson itself. So with that, let's begin. So I said that the point of today was to help you get started. So this is what I'm going to cover. I'm going to talk about what makes Haskell what it is, all the concepts that are the core of the language, which is going to be mostly a functional programming 101. I'm going to talk about the syntax, because the syntax of Haskell is quite different from what you may already know: how to read function types, how to read the thing, data structures, what do they look like in a purely functional language, and at the end, how to write our own functions. So this is what we're going to talk about today. This is what we're not going to talk about. I am not going to talk about anything related to project environment, like what's Cabal, what's the Cabal hell, how do you avoid it? Should you use stack or stackage? What's the difference? All of that I'm not going to talk about, mostly because it's boring. As in, it's just project management and build management, and that it's not what makes the language interesting. I'm also not going to talk about anything related to Haskell at Google, Haskell in Google 3. And the reason for that is there is already some very good resources put together by the Haskell team regarding how to write Haskell at Google. There's the Haskell Code Lab at go/Haskell-Code Lab, which is all about writing Haskell code at Google. It has only one drawback, which is it requires knowing the language, which is what we're trying to do here. I'm also not going to talk about the advanced stuff. I am not going to use the F word. I am not going to use the M word today. And the reason for that is those things are in the language, those infamous things are in the language because they solve a practical problem. But if you have never faced the practical problem they solve, and if you're not used to read the weird syntax of Haskell, it's just going to look like abstract gibberish. And I know because I've tried. The very first version of this lesson covered everything which is in 101, everything which is in 102, all the way up to the M word, and I tried to fit that in 2 hours. My poor teammates went through this, and I've promised to them I would mention their sacrifice every time I facilitate 101. So yeah, you need to first be used to the syntax and see what problems you face in this language before you can see the use of the M word. Yeah. Perhaps towards the end. The thing is, you actually don't need it to start writing your own programs. So I might talk about it a bit. So, but not today, clearly not. So that's the topic for today. The prerequisites, I'm assuming programming knowledge from all of you, because I'm going to compare Haskell to a lot of other languages, mostly C++, Python, Go, Java. And of course, if you already know a functional language, if you already know OCaml, for instance, it's going to be easier for you to follow. And you will need to install the compiler and the Haskell platform to be able to compile the code labs and do the exercises. If you have installed the Haskell platform, you now have GHCI on your computer. And GHCI is your new best friend. So GHC is the Glasgow Haskell Compiler. It's the one true compiler for Haskell. It's the only one only used. It's so ubiquitous that its nickname is the Glorious Haskell Compiler. And GHCI is the interactive version. It's the REPL for Haskell. And you can use it for almost anything. Inspect types, look up the type of functions, type expressions, see them, debug your code, step in it, like profile your code, everything. So basically, open GHCI whenever you start writing anything in Haskell. You can even open it and try typing the stuff which is on the slides. It might not always work, but could be interesting. So let's begin. What's Haskell? Well, if I read the slide, Haskell is a strongly statically typed, purely functional, lazily evaluated, general-purpose programming language. That's quite a mouthful, so let's break it down. I think two of those I don't need to explain. General purpose is something you all know what it means. It's important to stress because some people have this idea that Haskell is only good at like background computations, scientific computations, crushing numbers, that kind of stuff. And sure, it's good at that, but it's not only good at that. It's also being used for video games, window environments, front-end servers, back-end servers. It's a general purpose language. It can be used for anything you want. In the same way, I think strongly statically typed, it's not something I need to explain. It's one of the main features of the language, but it's not one I need to explain to you. I think all of you know what those words mean. However, purely functional and lazily evaluated are the interesting ones, and the ones I'm going to talk about. Before that, this is what Haskell is. Let's talk about why it's not. Firstly, it's not a silver bullet. This thing here, those 3 hours, are not a way for me to bring you into a kind of cult or something. I am not trying to give you fuel for flame wars. I am not trying to say Haskell is better than all the other languages and you can forget all the others. It's a tool. It's a language. It has upsides and downsides. I just happen to like it. The other thing is you might have heard this like legend of you need to have a PhD in math and know category theory to be able to write anything in Haskell. And that is simply not true. It's true that it borrows a lot from ideas from category theory, but you don't need to know category theory to write Haskell. Of course, if you know one, learning the other is going to be easier. But again, you don't need to know one to learn the other. I mean, I'm the proof of this. I know nothing about category theory, and here I am teaching Haskell. So yeah. And last but not least, clearly, Haskell is not hard. You might have heard it's hard. It's not. It's just extremely different from everything you already know if you only know imperative languages. If you only know imperative languages, you're going to be stuck at Hello World, which is kind of frustrating. But it's not because it's hard. It's just because it's a completely different way to approach programming. A few years ago, there was a poll in which people that write code for a living were asked to rank languages in different categories, and Haskell ranked first in 2 of them. The first one was learning that language changed the way I program in other languages, and the other was learning that language made me a better dev overall, because it makes you learn a completely new way to approach programming. So what does it mean to be purely functional? Through the slides, I'm not going to try to go too deep in theory. I'm going to try to stick at like the programming level. What does it mean for you to write code for a language like Haskell to be purely functional? Well, to start with, everything is a function. It's not object-oriented. We don't have inheritance. We don't have all those classes and stuff. I mean, we have data structures and functions. That so far, it's fine. We've all written some C and survived. So the idea of having only functions and structs is something we kind of know. The syntax, we're going to talk about it later, but it kind of looks like the syntax of math. On the right, you have the mathematical function f from the set of all integers to the set of all integers. That to an integer x associates the integer x plus 1. On the left, you have the Haskell version that takes the function f that takes an int, returns an int, and f of x is x plus 1. So pretty similar. We'll talk about the exact syntax later. So purely functional means everything is a function. So far, so fine. Well, it also means everything is immutable. If you know C and C++, it means every single thing you use is const, no exception. If you look at this example, I'm saying let a equals 3 in a equals a plus 1. And that thing doesn't even compile. It's not that it doesn't compile because I'm trying to assign a plus 1 to a, and if I were to try to assign to b, it would work. It's because this assignment operator doesn't even exist. When I say let a equals 3, it's a mathematical truth. So trying to say a equals a plus 1 would be absurd. When you create something, it never changes again. You never mutate anything in place. Which also means if you have a big struct and you want to make a modification to it, you have to create an entirely new struct that bears a modification. That sounds completely inefficient, but we'll talk about performance later. So, okay, we have only functions. They can never mutate anything in place, which means we only transform data and create new variables, well, variables, instead of mutating anything. That's kind of weird, but okay. Let me crank it up one notch. Everything is an expression. If you think about it, to have loops, which is the usual control flow thing, we need to have variables, things that change over time. Since everything is constant, well, we can't have loops. And indeed, we don't. We have only recursion. There's no loops in Haskell. And to go even further, there is no statements. You used to have statements line by line, separated by semicolons. That's not the case here. Here, the core of your function, the body of your function is an expression. That's all it is. So the if construct of Haskell is itself an expression, like the ternary operator of C++, or the weird value if condition else other value of Python, which means you can assign the result of an if, you can do transformation on the result of an if. And if you're thinking, well, that let A equal something in something construct, that's a statement, right? Well, nope, that's an expression as well. Of course, saying let B equals 2 in B is completely useless. The point is just to showcase you can use that let in construct anywhere you have an expression because it is an expression. Even the switch case statement is an expression. So purely functional so far means we have only functions all the way down. They never mutate anything in place. And everything is an expression. We have no loops. We have no usual control flow. That's kind of weird. But this slide is not finished yet. There's one more thing. We have no side effects in Haskell. What does that mean? Well, it means, if you look at this function foo, its type means it takes an int, returns a string. Having no side effects means it cannot write to the database, it cannot read from some input, it cannot depend from some global mutable state because there is no such thing as global mutable state, which means it has some very interesting properties. Since it cannot depend from anything outside of it, because there is no such thing as side effects or mutable global state, it means if you call foo twice with the same argument, you will get the same value out of it twice. Which means testing foo is trivial. You cannot forget to initialize something outside of it, because there's no such thing. If you refactor code that uses foo, testing that your refactored code behaves just like before is trivial as well. It makes reasoning about your code and testing your code trivial, which is great. We love that. There is just one drawback, though. We kind of like side effects at some point, because if our programs are just able to compute stuff in memory, but are never able to read from the command line or like write to a file or something, they're kind of useless. And the thing is, I've lied to you. It's not that we don't have side effects. We do. But when we do have them, they are explicitly stated. If you look at this function, read file, it's part of the default function, the prelude module, which is always loaded by default. And read file, the type informs you what it does. It takes a path to a file and returns the contents of the file, which is something which is full of side effects because like the file might have changed between two calls to the function, or the file might not exist. Like you can't guarantee that calling it twice will give you the same result out of it twice, of course. But if you look at the type, the argument, which is the path to a file, is a string, but the output, the content of the file, is not a string. It's an IO string. When you see types separated by spaces, think of IO of string, it would be brackets in C++. IO is a generic type, and string is its type argument. So it's an IO of string. And what's IO? Well, IO is a special type given to us by the language and the compiler that has one very important property. Every single side effect is in IO, which means that if you have code that don't use IO, that doesn't touch IO, we call it pure because it still has all the benefits I mentioned. Code that is outside of IO does not have side effects. If you call a function twice with the same argument, you will get the same value out of it twice. Testing it is easy. Refactoring it is easy. Same thing. However, as soon as you enter the IO realm, well, you're in the impure realm, and side effects might happen, but at least they're restricted to this IO part. Yeah, sure.
Why is IO part of the result type and not some kind of like namespace for the read string function?
Basically, it works kind of like a container. as in it wraps your value to indicate, to contain, to limit what you can do with it. And since you can only access stuff within I/O with a very specific set of functions which are provided to you but you cannot extend, it enforces at compile time that you can only do what you're allowed to do with I/O. Basically, what this means is that when you write your own programs, the core logic of the program is usually pure. Like you do all your business logic in pure code, which means you can easily test it, easily refactor it, easily prove assertions on your code, which is nice. And the outer layer, like main, is impure and connects your logic, your core program, to the outside world. This idea is not completely new. If you think about it, in object-oriented languages, the pattern of dependency injection is kind of similar in a way. As in, your logic, your module is completely independent, knows nothing about the outside world, completely testable in isolation, and your outer layer connects it to the rest of the world by injecting the dependencies. It's kind of the same idea here. The core of your logic is, the core of your program is pure, the outer layer is impure. The main difference is this logic here is enforced by the compiler. And the way it does that, what I'm trying to say with pseudo-mathematical notation here, is that we have functions provided to us that take something which is not in I/O and put it in I/O. Take something pure and make it impure. But there is no function that takes something impure and make it pure. We can never get out of I/O. If you think about it, pure is a strong requirement. Pure means there was no side effects involved in making this value. While impure means, they may or may not have been side effects. It's a lack of requirements. So taking something which is pure and saying it meets a lower bar is easier. It's easy, it's doable. Taking something which is impure and pretending it meets the strict requirements of being pure is impossible. If that seems weird to you, think about member functions in C++. When you write a member function in C++, you can mark it as const. If you do so, you're telling the compiler, this function will not mutate the state of the object, which is a strong requirement. If you do so, you cannot call non-const member functions, even non-const member functions that would not mutate the state of the object, because that would violate the requirements you've asked the compiler to check. Which means if you have to call a non-const member function, then your non-const member function becomes non-const as well. I/O is the same. I/O corrupts. If you're writing a function and you have to call something which is in I/O, since the result you will get is in I/O and you can never extract the stuff out of I/O, it means the result of your function will also be in I/O. Okay, roughly so far? We are not going to cover much of I/O today. Most of the exercises of 101 are going to focus on only pure code, getting you used to the syntax, because dealing with I/O, it's its own thing. So that's basically what it means for a language to be purely functional. Let's talk about laziness. I mentioned that Haskell was lazily evaluated. So what does that mean? Well, basically what is on the slide, as in we are used when you in most languages for stuff to be evaluated right away. For instance, in Python, if I say A equals a gigantic computation, the gigantic computation is performed, the result stored in memory, and that part of the memory is named A. And if I print A, it doesn't need to compute anything, it just reads A from memory and prints it. In Haskell, not so much. If I do A equals a gigantic computation, it returns immediately. And when I do print A, well, now it needs the value of A, so now it does the computation, and now it prints A. Everything is deferred until it's actually needed, which has the interesting side effect, if I may say so, that something which is not used will end up not being computed. One of the main drawbacks of laziness is that it's super weird. We are not used to thinking of computation that way. We are not used to have to think of everything being delayed and deferred. However, there's one thing, one basic thing, which is the same in C++, in Java, in Go, in Python, in Bash even, the same in all those languages, which behaves kind of lazily by default, as in it defers some computations until they are actually needed. And it's the same in all those languages. Can someone guess what I'm talking about? Yeah? Not exactly, because that's not the core part of the language and it differs from language to language. I'm thinking about a thing which is literally the same in all of them. Yep. Sorry, binary what? By conjunction, do you mean like Boolean operators? Or yeah, that is absolutely the answer I was expecting. We've all written that kind of stuff in C++. where we test whether a pointer is null, and if it's not null, some condition on the value inside the pointer. If that AND operator were a normal function, both arguments will be evaluated and passed to the function, and it would crash every single time the pointer is null. The only reason why this works is because it short circuits, which means if the first part of the AND operator is enough to compute the result, it does not compute, it does not evaluate the second part, which means the evaluation of the second part is deferred until it is actually needed. Think of this logic of short-circuiting, of waiting until we actually need the thing to compute it, apply it to every single function, and that's what Haskell does by default, which I know is weird. So let's talk about the pros and cons, because I've been saying it's weird, I've been saying it's non-intuitive, and I think it is. So why do we want it? What are the pros and cons of having laziness by default in the language? Well, oh, sorry, I forgot I had that slide. I always forget it. I try to keep light on theory, but basically in most languages, eager languages in which evaluation happens immediately, when you call a function, arguments to the functions are computed, and then the function is called. In lazy languages, first you inline the function, and then when you need them, you evaluate the arguments. So the pros and cons of laziness. Let's start with the cons. Memory pitfalls. As a beginner, it's something that's going to hurt you. Since laziness makes memory usage a bit harder to predict, at some point you will try to do reduce on a gigantic list of things, but you will forget that your accumulator during the reduce is actually itself lazy. So instead of having an accumulator that's getting updated while you go through the list you're trying to reduce, your accumulator is just a gigantic expression which is growing in memory, and you end up with a stack overflow. There are, of course, ways to avoid this, but as a beginner, it's something you will see at least once. The thing is, some purists deem that Haskell is not a true lazy language because it's not always lazy. It's just lazy by default. We have ways in the language to say, I want this thing here to be strict because I know what I'm doing and I know I want to avoid a stack overflow here. And usually the way you approach programs is to let laziness do its things, because most of the time it does great things. I'm going to cover that later. But sometimes at some precise points, you want to make things non-lazy, mainly to avoid that kind of memory pitfalls. The other kind of pitfalls that as a beginner you will see is parallelism pitfalls. Because imagine you have a bunch of computations to perform. You spawn 10 threads, you do all the computations, you join, you print, but you forgot that the whole thing is lazy, and when you do the print is when the computations actually happen. What your threads did was just to create the expressions. Whoops. Of course, the way to fix this is to use those escape hatches we have in the language to say, well, I want that thing to be strict here in the thread to make sure it happens when you want it to happen. Basically, we can force the evaluation to happen when we need it, but by default, it just waits until the last possible moment. Okay, I've been talking only about the fact that it's weird, non-intuitive, and the pitfalls for beginners. Why do we want laziness? What's the good that comes out of it? So my slides read huge optimizations, and it's quite an understatement. Basically, laziness is not the strong guarantee that the compiler will wait until the very last possible moment to compute your expression. It just means there is no strong guarantee as to when the computation will happen. It will just happen before you need it, probably the last possible moment. Which means it gives the compiler a lot of freedom. The compiler is able to rearrange your code to make the computation happen wherever it's efficient, because it doesn't need to compute it immediately. So I've been talking about the fact that when you have a gigantic struct, if you want to make a change to it, you need to make a copy of it, because we never mutate anything in place, right? Well, in an eager language, that would be horrible, because we would create lots of copies of the struct, which would have to be committed in memory, because computations have to happen immediately. But here in Haskell, if I have a function that creates a struct and then modifies it 10 times, but at the end of the function only returns a field of the struct, and that function is pure and has no side effect, well, the only thing that matters is the field. And since the compiler is not required to make the computations happen immediately, what the compiler can do is inline all your code, remove everything, never commit the struct in memory, and just generate the equation, which generates the field that you want. That's all. And remove everything else. So basically, the compiler has a lot of freedom thanks to laziness, because it removes most of the constraints that are associated with like computations in other languages. And basically, purity and laziness work together. As in laziness, sorry, I'm just going to finish this and then I'll take your question. Laziness gives the compiler a lot of freedom, and purity informs the compiler. As in, purity gives the compiler so much information to like know what your code is doing that it has both the information and the liberty to like tear through your code and optimize it away. Yes? Yeah, in practice, it really does that. And you will have, like, one of my favorite examples is one of the first chapters of parallel programming in Haskell. Same example of like spawning multiple threads and forgetting about laziness. The author of the book spawns several thousand threads to compute sudokus, and at the end of the functions, just print the length of the list of results. The compiler realizes that the length of the list of results is the same length as the list of inputs, removes the entirety of the code that does all the parallel computations, and prints the correct result without spawning a single thread. Optimize all your code away. Because the compiler is able to verify that the result you want only requires that small computation and none of all the things you've written. The compiler will tear through your code. In the end, Haskell is quite a fast language. I wouldn't say it's a selling point, like you want raw performance, use Haskell, but it's pretty fast. It's in the same ballpark as C and C++ rather than being close to Python. And the thing is, I've been saying like purity and laziness work together because like both of them inform and let the compiler choose what it wants to do and like optimize your code heavily. But it also works the other way around. Laziness enables purity. As in, we get all the benefits of purity without having to pay a huge performance cost for them. Because again, in an eager language, having to make copies of structs all the time would be horrible. And the other, yes, go ahead.
So basically, Haskell is fast because everything is computed, everything that you can compute at compile time is computed at compile time?
Mostly more because the compiler has such freedom and so much information that it can optimize your code heavily. Because again, in C++, for instance, if you have a function that returns void, you cannot just remove the function call entirely because you never use the function result, because it might perform side effects. But here, if you never use the result of the function, you can just remove the call entirely. Yes? There used to be a way to compile to C and see what the C-generated code looked like. Usually not really. Like performance tuning and inspecting what your code does is another subject entirely. Yeah?
That question, so what is the team behind the compiler? Is there like lots of people heavily working on it, or?
Yeah, it's mostly open. It's mostly like the thing is, there is just like C++, like new versions every 10 years or something. But since GHC is the only compiler, the team that works on it has a lot of new features that keep happening. Like there's a serious work being done on it. And more interestingly, in the last 5 years or so, the FP Complete Foundation has been doing a lot of work towards making Haskell more mainstream and more enterprise-oriented. And they've changed the entirety of the package ecosystem. It used to be only Cabal, and Cabal was a mess. And they've released Stack in the last 3 years, more or less, which is great and works perfectly well. They've released new editor modes for most of the common editors. They're working on a new IDE for it. They're working on like cleaning some old packages. There's a lot of work being done towards making Haskell a better language. So yeah, it's well maintained, heavily supported, and actually increasing in size rather than diminishing in size. Yeah, there was another question, I think. No, okay, perfect. So there's one last bonus of laziness. There's a few theoretical results regarding eager evaluation and lazy evaluation. One of them, which is interesting, is that as long as you have good caching, you will have not more reduction steps between eager evaluation and lazy evaluation, but a more fun one, and sometimes useful, is that there are things you can express in lazy languages that you cannot easily express or sometimes not express at all in eager languages. And one thing we get to express easily in Haskell that would be harder to express in like eager languages is infinite structures. What this silly example does, and again, it's very silly, but it's mostly for fun, is on the first line, I'm creating the infinite list of all the numbers, all of them, the infinity of them. It's the infinite list of 0, followed by 1, followed by all of them. And this returns immediately because we do not need to compute the list right away. We have the expression that generates it. That's good enough. In Python, generating the list of all integers would take quite some time because there's quite a lot of them. On the second line, and this is big ints, not integers, so it grows to infinity. On the second line, I'm creating the infinite list of all the numbers squared. And I'm doing this by applying the function to the power of 2 on the entirety of all the infinity of numbers. And same thing, it returns immediately because we do not need to compute anything right away. And on the third line, I'm taking the 5 first squared numbers, but taking the 5 first does not require computing the entire list. So this works. If you have tried typing this in GHCI and you have tried evaluating one of the infinite lists, well, then GHCI has to evaluate the entire list and is now shouting numbers at you and it's Control-C to stop it. Okay, so that covers mostly the functional programming part, what it means to be purely functional, what it means to be lazy. Let's talk about function types. So those are the red slides. Those are the most important slides of today. You can forget everything I've said before. Forget everything that comes after as well. Those slides are the only one that matter. If you remember one thing from today, remember this slide. Because this slide is about how to read function types. And since everything in Haskell is about functions, if you know how to read function types, you're mostly good to go. So we've seen function types before. I've used the colon operator in Haskell is used to mean the thing on the left, the name on the left, has the type on the right. It's used for two things. It's used for declarations, when you declare something new, or when you have an expression which is ambiguous and you want to tell to the compiler, I want it to be of this type. So in the slides, I use it quite liberally to mean, again, the same thing. The thing on the left has the type on the right. So here we have a function f whose type is int arrow list of int. The bracket is the built-in list type. Of course, in actual Haskell code, you would type dash angled brackets, but I have a prettifier for my slides. So we've seen before functions that have an input and output, they will have only one arrow. Here we have two arrows. Does that mean this is a function that takes a function as an argument? Is it a function that returns a function? Is it a function of two arguments, or does it return two things? What do you think this is? What do you think this type means? There are two different answers I would accept.
Function that returns a function and so on and so forth.
Yes, that is one of the two good answers. I would also accept a different answer. Yeah. It's indeed a function of two arguments. So how can both be true at the same time, being a function of two arguments and a function that returns a function? Well, the name Haskell comes from a guy who has a logician, Haskell Curry, and his first name was used for the language. His last name was given to a thing he theorized, though I've seen some people claim that he was not the first one to theorize it, but history has remembered his name. And currification is the idea that in math, a function of several arguments can be expressed as a chain of functions of one argument. As in, a function of two arguments can be expressed as a function that takes one argument and returns a function that takes the second argument, which itself returns the end result. And that's the way functions are implemented in Haskell under the hood. Of course, the language allows us to think of functions such as f as function of two arguments, and you will hear me talk about functions of 2, 3, 4 arguments all the time because it's easier for us to reason about them that way. But under the hood, every function only takes one argument, which is why the arrow for functions is take one thing, output one thing. What I'm trying to say is, saying that f takes two int and returns a list of int, and saying that f takes one int and returns a function from int to list of int, as far as the compiler is concerned, means the exact same thing. The compiler will not distinguish those two lines. They mean the same thing to it. Okay, with that, more or less? What we gain from this, except from like having only arrows because all functions take only one thing and output one thing, is we get partial application for free. Since functions that look like they take several arguments actually only take them one at a time, it means we can give the arguments one at a time. So f takes two arguments, but I can call f on only one. So function application is space. You don't need to surround the arguments with parentheses. So if I call f on one, well, I just gave only one argument to f. And the type of this expression, f of 1, is function from int to list of int, which means I can use this expression, f of 1, as a function itself, and call it on 2, and I would get a list of int. But again, since the language allows us to think of f as a function of 2 arguments, I can just write f12, and that's what I would do in most cases. If that helps, if it doesn't, you can ignore this. The function arrow is right associative. Space, the function application, is left associative. Is that clear for everyone? Yes?
What about 0 arguments?
Well, it would be constants, more or less. You just evaluate the thing by calling its name. Like if a is an int, you could see it as a function of 0 arguments. Any question on this? This is the most important slides. We will stay on this one until everyone has asked all of their questions. Please do ask questions. You're all fine. Yes, go ahead.
How will I express that I want my first argument to be a function?
We are going to see that in the next slide. But basically, you surround the arrow with parentheses to make it explicit. But we're going to see that in the next slide. Okay, perfect. No other question? You're all fine with this? This idea of functions only take 1 argument, we can give them one at a time and so on? Fine? Well, perfect. It's time for a quiz then. I'm going to show you some function types, and I'm going to ask a volunteer to explain to me what the function type means and what would be a good name for that function. I've seen people already guessing names. If you're already guessing names, it means you're already knowing the answer, and it's not you I'm interested in asking. Just a small information, when you see lowercase letters in function types, there are type parameters. You can think of this as template type name A, type name B. A main difference between C++ and Haskell, one of the main differences is if you write a template function in Haskell that expects any type name A, you can depend on some properties of A, like being able to be default constructed, or being able to be compared for equality, or being able to call plus on the value of type A. And you don't require to declare it. If you just try to instantiate that function with type A, it doesn't meet requirements, it will just fail to compile. In Haskell, not so much. If we require something out of the type A or B in this function, it needs to be explicitly stated at the type level. Here, there is no preconditions whatsoever, which means this function here works for absolutely any type A, any type B. We know nothing about those types. Maybe we can't do plus on them. Maybe we can't default construct them. Maybe we can't even instantiate them. Maybe there's no possible value of those types. We know nothing about them. So someone who doesn't know the answer to guess yes is map. Is that clear for everyone? Okay, perfect. Good session today. Perfect. So yes, the first argument is a function from A to B. This is how you would take a function as a first argument. You surround the function itself with parentheses. You surround the arrow function with parentheses. I hope that answers your question, more or less. So yeah, the first argument is itself a function from A to B. The second argument is a list of values of type A, and the end result is a list of values of type B. And what this function does, of course, you could create such a function that ignores the 2 first arguments and returns the empty list. But yes, the most commonly known function that has this type is map. And what it does is transform the list of A's in a list of B's by applying the transformation function on every single element. Yes?
I'm guessing the answer is no, but I'm asking anyway. Is there a way to express further constraints at the type level, such as, for instance, here, that the returned list probably has the same size as the second argument list?
So you can express at the type level constraints on the types, not on the values, by default. So saying, like, I require type A to have such method, yes. We're saying that list must have this given size, which is a constraint on the value. No, you can't, by default. There are language extensions, which are non-standard, that give the ability to express such conditions at the type level, at the comment level, more or less, and then the compiler checks them, but it's completely non-standard and not covered in today. There's a thing called liquid Haskell, which allows you to prove assertions on the values themselves instead of just proving assertions on the types. But it's completely non-standard. It's fascinating, though. I recommend checking it out. Okay, so if you've all guessed map, this one is going to be trivial to guess, right? Sorry? Yeah, it is indeed filter. Is that clear for everyone? This is a function that takes as a first argument a function from A to Boolean, takes a list of A's, and return the list of all the A's that passed the predicate. Of course, it could be also filter not, but bear with me. Again, the point of the slide is not to make you guess what function do magically, it's to make you practice reading function types. At this point in the slides, I am sorry to say I have to talk about the curse of Haskell. There is a curse which plagues beginners and even experienced developers. In Haskell, you can create your own operators. And sadly, people do create their own operators, which means you have to review some code, some of it written by you, that contains horrible operators which are completely unreadable, because you can. And because you can doesn't mean you should, but you can, and people will. So there's a lot of operators in Haskell code in the wild, and I'm going to use these slides to make you guess two of the most commonly used ones, because you will need to know about them, because if you try to read any kind of source code in Haskell, you will see them. So what the difference between operators and functions in Haskell is just the name. As in, operators are just functions. The compiler treats them as functions if they contain letters, and the compiler treats them as operators if they contain symbols. That's all. If you want to use an operator as a function, to give it as an argument to another function, for instance, you need to surround it with parentheses. That's also the case when you declare its type. So if we were to declare the type of the dollar operator, which already exists, we would have to surround it with parentheses, which is what we do here. Can someone guess and explain to me what this operator does based on its type? Sorry?
Applies the function test.
That is right. If you see it as a function of two arguments, it takes a function from A to B, it takes a value of type A, and returns a value of type B, and since we know nothing of the arguments, the only thing it can do is apply the function to the value. If you see it as a function of one argument that returns a function, it takes a function from A to B and returns a function from A to B. We don't need dollar to apply functions to values. We have seen that it's space to do that. So what's the point of dollar? It looks completely useless, right? Well, it's syntactic sugar. Let me show an example. Here in this example, I'm trying to apply the function fun to the sum x plus y. Since function application has the highest priority and binds first, if I were to remove the parenthesis in this example, it would be fun of x plus y instead of being what I want, which is fun of x plus y, which means I have to surround the argument with parentheses to make sure it gets computed first. But the thing is, Haskells don't like parentheses much. This is Haskell, not Lisp. We can use dollar to remove them, because basically dollar is simply function application, but with the lowest priority. So everything on the right of it is going to be computed as an argument. Everything on the left of it is going to be computed as a function. And then the function on the left is going to be applied to the argument on the right. It is simply syntactic sugar for function application without parentheses. It is used absolutely everywhere in Haskell code, which is why you need to know about it. It has one nice property, though. If you're calling several functions on the result of the previous function, if you use parentheses, you will have like 5 or 6 parentheses, closing parentheses at the end of the line. If you use dollars, you will just have like a chain of proper functions from right to left, but still. Okay with this? We'll see a lot of it during the code lab. Yes?
Let's say I have two functions,
Mm-hmm.
one is 2.
Mm-hmm.
And I want to calculate the sum of that 1 plus f2, and both functions again use two parameters a, b, c, and d.
At some point, there's only a few limited things that dollar can do. We'll see. I mean, the best way to answer the question is, I think, to wait for the code lab, because you will see how to use this function, how to use dollar, and I can show you some examples of this. Yes?
Question is, can you completely eliminate parentheses?
Not completely, sadly. Sadly, because all those pesky parentheses, but you can remove a lot of them already. Usually when it's not the last argument, you can't, because like dollar is used for a function and an argument, which means it can only be used for the last argument of the function. So you cannot remove all parentheses. A lot of them, though, but not all of them. The other operator I want you to try to guess is the dot operator, which is completely unrelated to the dot in object-oriented languages, because, again, this is not an object-oriented language. Can someone guess what this does? There is a formal word for it, but I would accept any non-formal word. Yeah?
Composition.
Composition is indeed the formal word I was expecting. Okay, good class today, which is great. So indeed, this takes a function from B to C, a function from A to B, and what it does is return a new function which combines both. We talk about function composition, and we take an A and apply the two functions and give you a C at the end. The point of this is we can create new functions by just combining existing functions without having to use lambda functions or declare new functions explicitly. For instance, we have seen filter, but if you want to try to filter a list to keep the elements that do not match a predicate, instead of having to introduce a new predicate that does the opposite of the other one, or do a lambda that does not the other predicate, you can just say not.predicate, and it composes the two functions together and give you something that's written true if the element does not match the predicate. Why it's named dot is because it's inspired by the circle operator of math, where f circle g of x is f of g of x. And basically what I mean is, if you have a function show that takes some stuff, returns a string, you have length, which is a function that takes a string, returns an int. If you compose them by saying length.show, it's gonna, this expression itself is a function of type take a stuff, returns an int. Okay with this? Basically, both with dollar and dot, we build pipelines. We are able to say, well, apply this transformation, then apply this transformation, then apply this transformation, and so on. And yeah?
Whether you want to combine the dot and the dollar sign.
You could, one thing you could do, for instance, is create a chain of functions on the left-hand side of the dollar operator, have a dollar, and then apply the argument to this chain of functions you've just created. However, you could also just have a chain of dollars. It's uncommon to combine both, but it might happen. Again, we'll see examples of this during the code lab. And if that idea of we build pipelines of changes by chaining functions that transform an argument seems weird to you, well, if you think about it, things that take only one input and return one output and chaining them to create better programs out of simple functions that do one thing and do one thing well is kind of a thing we do every day, more or less. Except pipes in Bash go left to right, and both dollar and dot go right to left, which I know is different. But that's basically the idea. Okay with this? Those were the red slides. Those were the important slides. You can forget everything else. And since you're absolutely fine with reading function types, well, there's one more quiz. This one, I do not expect everyone, except, well, this is a good class today, so most of you might guess what this function actually does, but the point is not for you to guess what it does. The point is just to make you practice reading function types again. Can someone explain to me what the function type means? You don't have to explain to me what it does. If you do, it's perfect, but that's not what I'm expecting. Just expecting someone to read the function type and explain what it means to me, because, again, being able to read function types is the most important thing. Go ahead. Mm-hmm. But what does a function type mean? Okay, go ahead. Uh-huh.
So far accumulated thing type A, the next thing type B to the list, and B to the new thing type A, and then I would guess that the second argument is the initial value.
That is a way better answer than I was expecting. This is indeed a very good class today. Yes, the first argument is a function that combines an A and a B into a new A. The second argument is A, an initial accumulator. We have a list of values, and what fold L does is left to right. It combines this initial A with the first B using the function we have provided, which creates a new A. It combines that second A with the second B, which creates a third A, and so on until we have been through the list. It is indeed reduce. Again, if you haven't guessed what it does based on type, it's fine. I was not asking this. It was just to make you practice reading function types again, because again, being able to read function types is the most important skill we'll learn today. Okay, so done with function types. Let's talk about types themselves. There is a lot to say about type theory in Haskell, but I've promised I would stay clear of theories. So let's see some actual concrete examples. First, we have type, the type keyword, which is basically type def, and a weak type def at this. So here I'm saying the type point is simply a tuple of 2 ints, which means a function that expects a point will also gladly accept a tuple of 2 ints. A function that accepts a tuple of 2 ints will also gladly accept a point. It's a weak type def. You can say the same thing with list. A polygon is just a list of points. And interestingly, unlike C++ before C++ 11, we can have template type def, if you like allow me to say that, to phrase it that way. As in, I can say the type map has two type arguments, k and v, and the map of k and v is just an alias for a list of tuples of k and v. That's not the most efficient way of representing a map, but just to show you that I can use such a type alias declaration to then use map of int to string or map of string to anything. Okay with this? Okay, so that's not very interesting because it's just type aliases. How do we create actual new types? Well, before talking about this, let's think a bit. What does it mean to be a data type in a language which is purely functional and in which we have no member functions because we have no inheritance, no classes, no object orientation, anything. We have no setters because we never mutate a thing since after it has been created. We have no private members versus public members because, again, no objects really. What do we have? What matters in a data type in such a language? And the answer is, sorry, I was not asking for input on that slide. Sorry, I should have made that clear. But if you have a suggestion.
Naming?
Name is important, yes. Not exactly. The only thing that matters is constructors. As in, how do we create the value? Since after it's created, it's never going to change anyway. The only thing that matters is how do we create it. And to go even further, since the compiler has complete freedom as to how the thing is represented in memory, or even not represented in memory, the question is not even how the layout is, the question is what makes an expression a valid expression of the type. So the way we do declare the data types is by listing the constructors, which are either constants or functions that create an expression of our type. Let's see some examples. To create a new type, you use the data keyword. And the way we do this is to say data, and then you give the name of the type, and then after the equal sign, you list the name of the constructors and the arguments if they take some arguments. So here we are seeing the type none, which has only one constructor named none, which takes no argument. It's a, what's the word? It's a convention when you have only one constructor in the type to give it the same name as the type, but you're absolutely not forced to do this. So here, what we're saying is that the only way to create an expression of type none is to call the none expression, which doesn't take arguments, which means the only possible value of type none is none. That types looks completely useless, and indeed it is. It could be used to represent the lack of information, because if a function returns you a none value, you know it's only going to be none because it cannot be anything else. And that's kind of how the non-type in Python is implemented. The only possible value of type non-type in Python is the constant none. So let's see a bit more interesting example. Constructors can take arguments. So here I'm saying the way to create a value of type minutes, the type minutes, is to call its only constructor, which is also named minutes, which takes an int. So minutes, despite being a constructor, you can see it as a function which takes an int and returns an expression of type minutes. And minutes 42 would be a valid expression of type minutes. This kind of type could be used if you have a datetime library and you want to make sure that every function takes minutes or seconds or hours instead of just taking ints and have people make mistakes using it. So again, this gives you no information about the actual layout in memory. It just tells you minutes 42 is a valid expression of type minutes. How do we get the 42 out of minutes? We'll see that in a few next slides. So that's it. This is the way we declare a constructor which actually takes arguments. Let's see a type that takes more than one constructor, because we have seen only types with one constructor so far. The Boolean type. A Boolean value can be created only with the two Boolean constructors, which are the two constants, false and true. I hope this surprises no one so far. But basically, yes, it means whenever you encounter a value of type Boolean, it has been created with one of the two constructors, which means there is no such thing as a null value. If you have a Boolean, it cannot be null. It's going to be always false or true. So we have no null pointers. There is no such thing as you expect it false or true, and it's actually none, and your thing crashes. So how do we represent the fact that we might not have a value? Well, we use, I think, what is the most interesting type we're going to see today, the maybe type. C++ used to have boost optional until, I think it's C++ 14 that introduced std optional instead, inspired by boost optional. but that's basically the same thing. An optional value may or may not contain a value of the type. And this is the same thing here. This is a generic type. You can see that it takes a type argument. It's a maybe of A, and since there is no precondition on A, that A can be anything. It can be int, strings, list of ints, anything you want. And an expression of type maybe A is either constructed with the nothing constructor, which takes no argument and therefore wraps nothing, or with the just constructor that takes an argument and therefore wraps a value. Which means if you want to construct a value of type maybe int, nothing is a valid way of constructing it, just 42 is also a valid way of constructing it. And whenever you encounter in your code a value of type maybe int, it's either nothing or just an int, which means it is an optional value and you will have to handle the case of the missing value explicitly because you have to. We'll see how to use that in a few slides. Yes?
So this works nothing, just false and true, they are not reserved here in this example.
What do you mean, sorry?
So these are not like keywords of the language. So you could, instead of nothing, you can write any other word.
Yeah, absolutely. You are completely free to name those constructors as you wish. Of course, the Boolean type and maybe type already exist. But if you were to recreate them, you could try a maybe two, in which the constructors are named foo and bar, and it would do the exact same thing. The only thing is, of course, you can't have the same name of a constructor between two different types. That's the only thing. I mean, at the very least, not in the same module. So if you have already a type that has a constructor named nothing, you can't have a constructor named nothing in another type to create.
That's why there's none.
Yeah, exactly. I mean, none is a silly example I'm showing, but yes, like if nothing didn't exist, I could have named it nothing. But since nothing already exists and is a constructor for maybe, I had to choose another name.
For
Yeah.
clarification, the three statements below, are they statements or expressions?
Oh, they're just me using the current column thing quite liberally. They're not part of the declaration. You don't need to declare them. They're just me showing what the type of the things are. So nothing is a valid value of type maybe A for any A. Just the constructor is a function that takes an A and returns something which is of type maybe A. And just 42 is an example of maybe int.
Right. So the first two would actually be valid language statements, and would the last one also be that?
There would be, but not for declarations, because you don't declare the constructors explicitly. When you don't declare the type of the constructors explicitly, they are derived from the type declaration.
Yeah, so assuming we don't have the types.
Yeah, well, except you can, like the lowercase, uppercase things is meaningful in Haskell. Types have to start with an uppercase. Constructors have to start with an uppercase. And type parameters, like the A of maybe A, have to be lowercase, and normal functions have to start with a lowercase as well. So, but assuming we didn't have this restriction, yes, you could declare nothing being some kind of maybe A, and nothing with a lowercase n, for instance, to just return the maybe A and we just return nothing, would be a valid way of declaring a function. We'll see more of the actual code when we start writing functions and in the code lab. Yes, of course.
Yes, the foreigners are built in language.
Yeah, the way my prettifier for the slides works is it transforms all the values and constants it knows being part of the language in green, and all the types it knows being part of the language as blue, which gives you a strong hint as to which types I've made up and which types are actually part of the language. So nothing, the type of nothing is maybe A. Which means for any type A, whether A is int or strings or anything, if a function expects a maybe something, you can give it nothing. Yeah. Okay, so far? One last example, the list type. Let's imagine we want to build a very simple linked list type. How do we express this in Haskell? Well, an expression of type list of A, for again, whatever A there is, we don't care about what is stored within our list, is either nil, the empty list, or a cell that contains a given value and the rest of the list. The cell constructor takes two arguments, the value and the rest of the list, which can itself be either nil, and we have reached the end, or a cell that contains the value and the next element of the list. So nil is a constructor, which is a valid expression of type list of A. Cell, the constructor, is a function that takes two arguments, the current value, the rest of the list, and returns an expression which is itself a valid list with the value appended at the beginning and at the end. And cell 0 followed by cell 1 followed by nil is a valid example of a linked list of int. Of course, we can use dollars to remove the parentheses. So why am I showing this weird linked list type? Because like this idea of we append values at the beginning is kind of weird. This idea of the cell constructor taking 2 arguments is kind of weird. Why am I showing this to you? Well, first, because it's interesting. It's a generic type that has 2 constructors, one of them being a constant, the other being a function whose one of the arguments is also the same value as the type. And also because that's the way the built-in list type is implemented. This actual line, this 5th line, would not be valid syntax because the bracket syntax is reserved by the compiler. But if we open our mind a bit, what I'm saying is the type list of A that you will see in the code is either the empty list, empty brackets, or the colon operator, because yes, operators can be constructors, which appends a value at the beginning of a list. So empty brackets is an empty list for any type of list. Colon is the constructor that appends a value at the beginning of a list. Take a value, a list, and just appends them. So 0, 1, the empty list would be a valid list. But of course, we would write it 0, 1. The syntax of list is super weird, which is why half of the exercises we're going to do today are going to be about lists. Okay, basically with this idea of we list constructors which give us the list of ways we can create a valid expression of our types. If that's okay, I can move on to how we actually use them. Okay so far? Okay, so one more thing before I move on to actually using them. Sometimes what we want is just a good old C struct. We don't care about having many constructors. We just want one constructor and a list of fields. Because sometimes that's just all we need, right? So we could just use this. I'm saying user has only one constructor, which is also named user, which takes a string and an int. So the user constructor would take that string and an int and return a valid expression of type user. The thing is, we don't know what the string is. We don't know what the int is. We don't know yet how to access them. And there is, thankfully, a struct-like syntax that allows us to just write this. User is still the same. It's still a simple type that has one constructor, user, that takes 2 arguments, a string and an int. But here we name them. And this does 2 things. One, it makes the declaration a bit more readable. And also, it creates 2 functions for us, username and user age, which are kind of getters. They take an expression of type user and they extract the field out of it, which is also why I've named them username and user age. They are created in the same namespace, and I didn't want to overload the name and age and names. Okay, with this, more or less, we'll see examples in the code lab again.
You put a function.
Yeah, absolutely. You can have functions as function as. What do you mean?
Like this something.
Oh, I mean, you could always, we'll see pattern matching right after, but you could always access the fields without needing the functions. But when you name the fields, it just creates a function for you that will extract the field out of the object. So if the object itself, the field is itself a type that has fields, you could call then the function that extracts the field that you want out of it. You can just chain with dollars the different extraction functions until you get the thing that you want. Okay, so let's talk about actual functions, because I've been talking for roughly an hour at this point, and we have still written not a single function yet. Which reminds me, I wanted to showcase some examples of how the actual one argument at a time thing works, but since all of you seemed fine with it, I think it's fine if I didn't show this. Too bad. Okay, so let's write some functions. How do we write functions in Haskell? Well, first we start by giving their type. This is optional, as in the compiler is able to figure the type by itself. It doesn't need your help. However, if you write a bunch of functions without ever giving their type, and if you just let the compiler infer the types for you, and at some point you use all of those functions together, if there's a type mismatch because you did something wrong somewhere, the error will be where you use them because they are incompatible together, which doesn't help you much. However, if you mark the type of every single function you write, when you make a mistake, the compiler will be able to pinpoint where you made the mistake. So it both makes the code more readable, and it makes the compiler able to give better error diagnostics, which means it's a warning to write a function without writing its type. Some IDEs are smart enough to just run the compiler, parse the warning, and insert the function type for you, because again, the compiler is able to figure out the type just well. It's just, for the code itself, it's better to write the type. So we do write the type of the function, and then we write its implementation. So here we're writing not, a function that takes a Boolean value, returns the other Boolean value. So what is not of x? How do we actually write the code? Well, we could use an if, right? I could say if x then false, that's true. but that's kind of ugly. A thing we can do is we can write several implementations of our function. We can write several expressions to be used. And what we can do is we can choose which expression to use based on how the value x was constructed. We know that x is a Boolean value. We know that the Boolean type has only two constructors, which means there are only two possible values for x, true and false. So we can use pattern matching and write the two cases. Not in the case where the argument is true, returns false. Not in the case of when the argument is false, returns true. Okay with this? Pretty simple, right? Let's imagine the AND operator doesn't exist. Of course it does, but let's imagine it doesn't, and let's re-implement it. So first, we declare its type. It takes two Boolean values, returns a Boolean value. What is x and y? Again, we can just write ifs and say if x, then if y, then true, else false, but that's disgusting. So let's not do this. We know we can do pattern matching, right? So let's do pattern matching. False and false is false, false and true is false, true and false is false, true and true is true. And that's quite verbose and not much better. However, what we can do is we don't need to list every single pattern. Patterns are tested in order by the compiler, which means what we can do is say, well, if true and true matches, then the answer is true. If it doesn't, fall to the second pattern. And if it's x, whatever x is, and y, whatever y is, the answer is false. There is one minor drawback to this version, though. It does not short circuit. Because to test whether the first line matches, it needs to check whether both the arguments are true. But the thing is, we don't need to match explicitly all the arguments. We can also write, well, true and y is just y, as in if the first argument is true, the answer is just the second argument, whatever it is, and we can defer the evaluation until the y is actually needed. And if we don't match that first line, whatever matches on the second line, we don't care. Whatever is true and false, false and false, false and true, we don't care. It's just going to be, the answer is going to be false. Yes?
It's false. Right?
Yeah, of course. Yeah, it's a true as a possibility, but yeah, x is never going to be true. We could write false here instead of x. It would change almost nothing. I mean, if you prefer, yes, there's nothing wrong with doing it. There's just one more thing. In most programming languages, declaring an argument, giving it a name, and then not using it is a warning, because you're like giving a name and then you don't use it. In Python, the convention is to prefix the name with an underscore to mean I know this argument needs to be here, but I'm not using it. In Haskell, underscore itself has a special meaning. You can have more than one underscore per implementation line, and underscore means I don't care. And if you don't use it, like if you give a name to those arguments you're not using, the compiler is going to give you a warning of you named it, but you don't use it. Underscore means I don't care what this thing is. You cannot use underscore in the expression, which means you are discarding the value, whatever matches, I don't care. Okay, roughly with pattern matching? Yes? Not really. The compiler will not generate a line for you, which is all the arguments with underscore, because you still need to specify what happens in that case, what is the return value. So the compiler is not able to say, well, I will insert a catch-all in the end of your function. The compiler will, however, give you warnings if you do not match all the possibilities. As in if your function like matches true but doesn't match false, or for more interesting types, doesn't match one of the cases, the compiler will give you a warning of your function does not have an output for all its input values. Oh. It will give you a warning, yes, like, hey, you named it and it's not used. Just like C++ would give you a warning of argument not used in the function, and you have to either comment it or remove it completely, or Python would do, like PyLint would do the same for non-used arguments unless you prefix them with underscores. Kind of the same thing. You name something, you don't use it, maybe something is weird. So let's see other examples of where pattern matching is useful. I have talked earlier about this minutes type, which is a simple thing. It has one constructor, takes an int, and wraps it. How do we get the value out of it? Well, let's take a small example. We're writing an add function that takes two values of type minutes and adds them, computes the sum of them. It returns a new value of type minutes that just contains the sum of the two ints. So how do we add two values of type minutes, mx and my? Well, we could try mx plus my, but we haven't made our type minutes work with the operator plus. That's one of the two material. So we can't do this. The thing is, we know that the value of type minutes was constructed with the only constructor of minutes, which is itself minutes. So we can use pattern matching, even though there's only one pattern, because we know that the first argument was constructed by using the minutes constructor on something that we will name X, and the second minutes argument was constructed by using the minutes constructor on something we will name Y, which means we can just return the result, which is minutes of X plus Y. And of course, we can use $, to remove the parentheses. Okay with this, basically? Pattern matching allows us to choose implementation based on the values of our arguments. It also allows us to deconstruct the arguments to know how they were built and to access the fields inside them. One last example, length, because again, the syntax of list is super weird, and the more you will see it, the easier it's going to get for you to read them. So again, lists are either the empty list, empty brackets, or a cell, which is a value, colon, the rest of the list. Let's write length. We want to write length, which takes a list of any A, we don't care, and returns an int, which is the length of the list. So we know that the value of type list is either the empty list or a list containing some value followed by the rest of the list. So we just write the two patterns. Length of the empty list is, someone said one once, is indeed 0. And length of a list which is made of the element X appended at the beginning of the length of the list XS is
1 plus length.
Indeed, you're a good class. It's easy for you. And yes, that's how we do things on list. We pattern match whether the list is empty or not, because list, just like any other type, has two constructors. Yes?
Is it like, let's say I have a list and I call length couple.
Sorry? It's?
I have a list
Uh-huh.
and I call length couple of times in different places. Is it going to be cached somewhere and it will not go and calculate the length of the list?
Most of the time, yes, it's going to be cached, yes. Depends on how much the compiler knows that you're trying to compute the length of the same list. But yes, if it can, it will cache it. Yep.
Very early on, you had this nice example of all the natural numbers and
Uh-huh.
express it as a list. If I want to check if the length of the natural numbers is larger than 42, will this make my program fail, or?
Yes, your computation will not terminate because the compiler doesn't know enough. It will need to try to compute the length to compare it to 42. However, what you could try is to take the first 42 elements and try to see if that has 42. You could try such a thing. But just trying calling length on the infinite list, yes, will never terminate, sadly. And I think that's all I have for you. I mean, you can't just do it by calling length on the list and then comparing the results to 42, because calling length would take an infinite amount of time. However, going through the list and stopping at the 43rd element and saying, oh, there's more than 42, is fine, because that thing doesn't require going through the entire list. And that's what I have for you in the slides. I'm going to show you a quick links for you, and then we're going to take a quick break in which I can answer all the questions that remain, and then we'll start the exercises. So links I have for you, I have two questions in the buffer. So the slides, if you want to have them, are at go/haskell-101-slides. If you want to try a GHCI in your browser because you don't want to install it on your computer for some reason, try haskell.org has a GHCI in the browser. If you prefer to read books, well, there's 3 of them I would recommend. Learn New A Haskell, which is written by someone who has a background in imperative languages. So it's really oriented towards, C++ or Java. Here's how Haskell works. It's a pretty good book. It has a few problematic examples, but if you ignore those, it's otherwise a pretty good book. Real World Haskell is a great book also. I really like it because every chapter has a small project with it that you can download and try. And every project is not an abstract thing like re-implement piano numbers or like weird containers. It's an actual useful thing. So each chapter shows you how to use the things you've learned in an actual useful way, which is nice. And the Haskell book is pretty new. I haven't read it yet, but all the reviews I've seen so far are extremely good, so I put it in the slides as well. And the last thing is Hoogle, and I have to show it to you. So as you can imagine, Hoogle is a search engine for Haskell, which allows you to search for stuff like if I want to search length, well, I will get that length takes a list of A, returns an int, and is defined in both prelude and data.list. But Hoogle has one more feature that makes it absolutely amazing. You remember that maybe type I mentioned before, which is the optional type. So if I have a maybe int, I may or may not have an int. If I want to extract an int out of a maybe int, I need to provide some kind of default value in case there is nothing in the maybe int. Well, what function does this? Let's imagine I have some maybe int. Oops. I have an int, and I want a function that combines both and gives me an int. Well, there's from maybe, it takes a maybe a, and an a. The from maybe function takes a default value and maybe value and so on. Google can search by type. And for beginners, this is a blessing because hey, I have those two things. How do I combine them? Search for a type, which takes those two things and returns what you expect, and you will get all the functions that match what you've searched for. That is just, Google is amazing. And with that, I think it concludes the slides part. It's 11:20. Let's say we're gonna start the exercises at 11:30, and in the meantime, I can take both of your questions. You had a question. What do you mean?
Like you said, you want to showcase something.
Oh, I want to showcase the minutes thing where we use pattern matching to extract the value of the constructor. I think that was the thing I wanted to showcase. Oh, sorry, yes, no, so something else that I wanted to show. I wanted to show this in GHTech. Is it big enough? Is it big enough, or do I need to make it bigger? I wanted to show, I completely forgot I usually show this. I usually show that we can create an add function that adds an x and a y. An add of x and y is just x plus y. And I'm going to make this on int because I don't want to deal with generic functions just yet. So that declares a function of 2 arguments, even if under the hood it's only a function of 1 argument. So the type of add is just takes to int, returns an int, and add 4 and 8 is 12. But the thing is, since add only takes 1 argument under the hood, I can completely create add 5, which is a function add partially applied to 5, and the type of this is, oops, sorry, I can't type. Function from int to int, and add 5 of 6 is 11. Because what happens under the hood is that I've declared add as being a function that takes 2 arguments, but as far as the compiler is concerned, it's exactly the same thing. It makes no difference as add being a function that takes 1 argument and returns a lambda function, they're introduced with a backslash, because backslash kind of looks like lambda, which takes y and will return the x plus y. This declaration, where add only takes 1 argument and returns the function, is the exact same thing, and the compiler sees absolutely no difference. That's the thing I wanted to showcase, which I forgot. But since most of you were completely okay with map filter and everything, I think that was okay for most of you. And anyway, we'll see that during the exercises. Yeah, sure.
There are a few slides like, for instance, defining the not Boolean.
Yep, this one?
The one before.
Uh-huh.
One after.
Ah, okay.
The one before, the one that has an if. So we define the ball type as like true or false. What happens that?
Oh, makes it work with if?
Yeah, like how does this bind to if?
Basically, the Boolean type is pretty fine. Like I'm showing its definition, it of course already exists. The compiler knows about it and expects the argument to the if to be of type Boolean, that very specific Boolean type that already exists.
So if in itself is a function that...
It's not exactly a function, it's more of it's actually a keyword. There's not a lot of keyword in Haskell, but if then else is actually like a few of them. But it requires a thing to be a type Boolean. You cannot give an int and expect that int to be converted to Boolean. There is never implicit conversions in Haskell. Well, never is a strong word, but almost never implicit conversions, and never to Boolean. Yeah.
I don't know how it works in Haskell, but for example, in TechTalk, if matches the first constructor. So
Interesting.
So I'm not sure about
Haskell, no, it's clearly a Boolean value. It will not try to reason anything about your type. It's Boolean value or nothing. The 2 cases I know where there is implicit conversion performed is from integer literals. Like if you type 0 something, it can convert to any of the number types it knows, either int or integer, which is the big int. That is kind of an implicit conversion, but it's fine. And the other case is when you enable a specific language extension, you can convert string literals to one of the different string types. That's the 2 only cases I know where an implicit conversion is performed. And it's from a literal, so it doesn't matter that much.
yeah, you can
Usually
It
fine.
just makes literals to belong to several types.
Exactly. Otherwise, I don't think I know of a single implicit conversion. So if you have downloaded the CodeLab file and you have unzipped it, whether on your laptop or on your workstation, you will see that it contains a CodeLab file, a main file, and a solution file. If you compile it using make or build, or Blaze as you prefer, it creates two binaries. One of them is the solution binary, which runs the test on the solution file, which contains the same thing as a CodeLab file, but with the solution. Don't peek into it, that ruins the fun. So of course, all the tests on the solution file should pass, which confirms that your installation is correct. And of course, running the CodeLab binary will run all the tests on the CodeLab file, and of course, all of them will crash because we haven't implemented anything yet. If you open the CodeLab file, which is the one in which you have stuff to do, it explains to you how to test your code and how to compile it. You can either run make and run the CodeLab binary, or if you prefer, and that's actually the way I would recommend you do it, you can open GHCI, do the magic set thing. That's because I do horrible things in main, don't worry about it. Load the CodeLab, load main, colon L is to load something. Just run main to run the tests. And colon R is the way to recompile something. It reloads all the things that had been loaded before. So if you have made changes to the CodeLab, just type colon R, it will reload the things, and just run main again to run the tests. The CodeLab is divided by section. Section 0, you have nothing to do in it. It's just to do a setup. I introduced the CodeLab thing, which is of type A, so it works anywhere, but it uses the built-in error thing, which just panics the program if evaluated, which means every time the code will try to evaluate something named CodeLab, it will crash, which is why all the tests fail. It starts with section 1, which is about deconstructing lists. All of the exercises are the form, I give you a function, I give you its type, and oops, this is, sorry, don't have a look. I forgot to unzip CodeLab.zip. So oops. The file I was showing to you contained the solution. Where is? Okay, we'll need to re-download it because, okay, let me give you 1 second. So go/haskell-101-CodeLab, which downloads a zip file, which I'm gonna move here. Oh, because I'm in the wrong folder, that's why. Okay. And hopefully, no, I'm stupid, sorry. I still need to unzip CodeLab.zip. Okay, yes, and now, hopefully, yes, there is no more the solution in the CodeLab file. Perfect, I can show you the section 1 without spoiling the answer. So the way this works, each exercise is mostly, I'm giving you a function, I'm giving its type, what it does, and I ask you to implement it. It's divided by section. There's 4 sections in total. Feel free to move on to the next section if you're already finished. There's some bonus things for people that go faster than the others. What I'm gonna do while you write code, while you work and I do nothing, is I'm gonna roam the room and look at your screens. Beware. And the point is, please do ask me all questions you have. If you're blocked on the thing, please do ask me for help. The point is like for you to try to write your own code. And every now and then I will go back here and give the answers to the questions and showcase different elements of syntax that I didn't want necessarily to show during the slides. If you have questions on the setup, if it doesn't compile for you, if you are lost, please do ask me. I will try to show, for the section 1, not much, but I'm going to try to show more interesting things, like several different versions I've seen. Like, for instance, for null, I've seen several people try, not today, but I've seen people try, saying, well, null of L is L equals the empty list, which is interesting, right? Well, because it could work. It could be, well, if it's equal to the empty list, it's true. Otherwise, it's not true, and that's perfect. Except this doesn't work. And the error message here will be super cryptic. So let me explain why this doesn't work. The equal operator to work on lists, is only defined on lists if the type A inside the list also has the equal operator. Because you cannot compare lists for equality if you cannot compare the elements for equality. Which means if we wanted to implement null that way using equal equals, we would need to say at the type level, actually A has equality since we're using equality on list. Here, we're not saying that A has equality. We don't know if it has, maybe it has not. Therefore, we cannot use equal equal even just to compare with the empty list. So what I was expecting here is, of course, to use pattern matching. Null of the empty list is true. And null of a list, which again, the pattern is written right here, is a value x followed by the rest of the list xs. It's a convention, not a rule. If you are matching the pattern of a cell containing the value and the rest of the list, if you name the value x, you name the rest of the list xs, x plural, if you will. It's a convention, you don't have to follow it. Of course, if we match this, which is the other constructor, then false. Of course, we don't use x and xs. We can just use underscore instead for both of them because we can use more than one underscore per line. And we don't even need to match the pattern because we know that if we didn't match the empty list, we know this is the only other pattern. We absolutely don't care about it. We can just use underscore and say whatever the list is, if it didn't match the empty list, then the answer to null is false. So head is an interesting one. It's considered bad design, but it's here for historical reasons. It's what we call a partial function, which means it doesn't have an output for every single input to the function. For some of the input, it crashes. It uses the error thing to just panic your program. So head of the empty list panics. We usually dislike partial functions because we dislike this idea of your code can crash, but this is how it was implemented historically, so I kept it that way for the exercises. So head of empty list doesn't work. What's the other possible way to construct a list? So what's the other possible argument, only possible case for an argument to head? It's a list that contains some x followed by the rest of the list that we actually don't care about, because since head returns the first argument, the first element of the list, head just returns x. And finally, tail. Tail is the exact same thing, as in it panics on an empty list. And tail of something which is not empty, which has some elements we don't care about, and the rest of the list is the rest of the list. Some people think that tail returns the last element, but it's made obvious that it's not the case by the type. It returns a list of A, not an A. Let me just check I didn't make mistakes. For section 1, it's unlikely, but for the rest, it will definitely happen. Okay. That's it for section 1. Onwards to section 2, recursion. So length, I'm not going to spend a lot of time on it because it was in the slides and most people go back to the slides and copy it from the slides. So I don't have a lot of interesting things to say. Length of the empty list is 0, and length of... Some people have tried something which I find interesting. It's not wrong by any means. It's not what I was expecting. To say, well, for a given list L, which we know is non-empty, it's 1 plus length of tail of L, where we remove one argument. It's perfectly fine. That's just, I was not expecting this, but it works. It just uses tail, which I always find a bit icky because we can just here, oops, sorry, I can't type. We can here explicitly match the fact that we know it's a cell that contains a value and the rest of the list, and then write 1 plus length of the rest of the list. The tail version is perfectly fine, and I have no problem with it. It's just not the one I was expecting you to write, because the point of those exercises is to make you practice pattern matching on lists. And I've made a typo here. That should work. So and or, there's 2 different ways to implement them. I'm going to showcase both of them. There's one that I prefer, but again, it's up to you to decide which one you think is better. So there's, of course, we have to choose, we have to match the empty list, because again, we have to have a base case for our recursion. And end of the empty list, so is it supposed to be true or false? The way I reason about it, I don't know if theoretically it sounds, but it's to say something which is true for every single element in the list is true then when there's no element in the list. Something which is true for at least one element in the list will not be true for an empty list. So end of the empty list is true, and or of the empty list is false. So what, oops, sorry, I can't type. What some people choose to do for an and or is not to write the second pattern as a generic pattern, but to match explicitly what Boolean value we have in the list. And say, well, if the first value is false, we don't care about the rest of the list because we can stop the recursion immediately and return false. Otherwise, if we have something else which has to be true as a result, then we can take the rest of the list and go recursively and say it's end of the rest of the list. This works perfectly fine, but you are doing pattern matching on the first element of the list through recursion. Another version, which I would personally find better, but it's completely up to you, is to actually match the generic case. You might have noticed I'm not a native English speaker, and the first time I give this lesson, I named them B and BS. I've been told BS means something else in English, and I don't care. Would be to say, well, how do we combine B itself, which is a Boolean value, with the recursive call of OR on the rest of the BS? Well, we use the OR operator. And since it short circuits, then if B is true, it's not gonna compute the rest of the recursion. I find this one slightly better because text is slightly shorter and still easy to read, I think, but which one you prefer is completely up to you. And finally, concatenation. You need a few more minutes, or are you okay with me spreading the answer? I take that silence as a yes, you're okay with me spreading the answer. So, concatenation. The trick is, again, that we are creating a new list because we never mutate anything in place. And the way we create new list is by using the colon operator, because yes, it's an operator which is a constructor, by appending values at the beginning of a list. We never append at the end of a list, which means we are gonna append stuff at the beginning of L2 instead of appending stuff at the end of L1, which means we don't need to break down L2. We absolutely don't. The recursion we need to do is on L1. So there's two possible cases. Either L1 is empty or L1 is not empty. In the case where L1 is empty, well, the answer is easy, it's L2, right? In the case where L1 is not empty, well, we know we'll have to append that X at the beginning of the result that we're gonna do. And it's a recursive function, right? And what's the rest of the list? What's the rest of the concatenation to which we append that X? Well, it's simply a recursive call of XS, the rest of list 1, concatenated to L2. This goes recursively through L1, and then appends the element of L1 one by one back to L2. Okay, perfect. So section 3, higher order functions. Let's start with map. So map takes a function from A to B, a list of A's returns a list of B's. So far, so fine. If we have an empty list, we have no value on which to apply the function, and transforming an empty list into a list of other values will still be the empty list. No surprise here. So how do we apply a function f on a non-empty list? Well, if we trust the types, f is a transformation function that takes an A transforming into a B. So if we apply f on an A element, we'll get a B element. We don't mutate things in place, so we have to create a new list. The way we create new lists is by using the colon operator to append values at the beginning of lists. And what's the list to which we want to append that new B value? Well, it's the recursive call of map itself with the same transformation function on the rest of the list AS. Okay so far? Since function application binds first, always, we can use the operator here without needing parentheses around the arguments, because that thing is going to be computed first. Well, I mean, not necessarily computed first because laziness, but in terms of operator precedence, this binds stronger, is a higher priority, and this is a higher priority than the operator itself, because function application binds first. So in filter, yeah, of course, sorry.
So the way I understood this task initially is that you have to implement it using fold functions.
Oh, interesting. Oh, that's, yeah. Yeah, fold and fold are, well, yeah, implementing map with fold is non-trivial to say the least.
So I implemented it with fold R, it works.
Okay. Yeah, fold R is a proper choice, yes, in this case. But
Yeah, the question is, I have to define like if it's two-line solution, so I have to define another function that just takes one element and creates a list with one.
You could use a lambda function. Probably no. Like you could probably write map of f and l. I have never tried to write it as a fold, so let me try to improvise here.
It's not real.
I mean, it's gonna be a fold R. The base case, so the combination function is gonna be a lambda, which takes the current value of the list and our accumulator L and appends f of a at the beginning of L. The base case is going to be the empty list. I'm going to name it differently to not be confused with the one we have as an argument to the function. And the list on which we do the recursion is going to be this. It should look like something like this. I'm not sure this. Let me check if this works. To be honest, if it works, I'm super happy. It compiles. No, it doesn't work. Why doesn't it work? Oh, because it uses fold, which I haven't implemented yet. Of course. But yeah, I was not expecting you to write it using fold. Yeah, absolutely. This is something I'm going to talk about later. But yes, you could absolutely define it that way. Well, map is something you never implement because it already exists. But in this case, I would definitely go for this version.
Yeah. We have to write the L.
Oh, that I'm going to mention later. But my recommendation is choose whatever makes the code more readable. And in most cases, not always, but in most cases, naming the arguments makes the code more readable. When you're dealing on lists, yeah, of course, the last argument is a list. You name it L. It doesn't add information. Maybe you can omit it. But otherwise, naming arguments is always better. Okay, let me proceed to the others. So filter, I introduced the guard syntax because pattern matching is nice when you want to know how a value was constructed, but sometimes you want to do some more interesting tests on the value you have on your hands. So what the compiler does is the same thing as for pattern matching. It tries all the guards one by one and selects the first one for which the expression evaluates to true. Otherwise, it's just a constant of type Boolean whose value is true. You could write true instead of otherwise, or 1 is greater than 0 here. Like anything that evaluates to true would be the same, but otherwise is just more readable. For once, we have chosen letters instead of symbols for Haskell, so that's nice. So what's the case we want here? Well, of course, filtering an empty list is always going to be the empty list because there's no element to filter. So we have two cases when we encounter some x in the list in our recursion. Well, either x passes our predicate f or it doesn't. So if I type f of x here, what's going to happen is if f of x is true, the compiler is going to select this implementation of filter. Otherwise, if f of x was not true and we fell down to that line, the compiler is going to select this line. Both of them are going to be mostly the same, as in we need to go recursively through the rest of the list. We need to call filter on the rest of the list. So both of them are going to have filter of f on xs. There's one key difference. In the case where x passed our predicate f, we want to append x at the beginning of that list on the way back to reconstruct a list that contains x. Okay with this? Finally, fold L and fold R. Okay, so if you're lost with those, the hint I was giving to people is trust the types. Some purists hate me for saying that, but sometimes just like making something that compiles by trying to see how you can make the types work together leads you towards the right answer. So here, what we want is combine the accumulator, the original accumulator, with the first element of the list, and then pass it as the new accumulator for the next argument, for the next element of the list. So, well, first, when we have an empty list, what we want to return is, of course, the accumulator. It means we have reached the end of the list. And also, we have no x element. So even if we wanted to create a new a element, we can't use the function. So the only thing we can do anyway is just return the accumulator. How do we do the recursion, though? Well, we know we want to combine the accumulator we have with the first element of the list. So we know we have to call FAX. That we know we have to do. However, what we want to do is use it as the new accumulator for the next element of the list. So what we do is simply call fold L recursively with the same combination function with that new accumulator that we got by combining the A and an X together as the new accumulator, and we go recursively through the rest of the list. For some people, it helps to realize I said any operator can be transformed into a function. The other way around is true. Any function can be transformed into an operator. If you surround a function by back quotes, you can use it in an infix syntax, which means this f function, I can use it kind of as an operator. In this case, I think it adds absolutely nothing whatsoever in terms of readability. But for some people, since my example was using an operator as the combination function, maybe it helps reason about which element, which one is the accumulator, which one is the element. If it doesn't, there's absolutely no problem with this. Just saying FAX is perfectly fine. And sadly, no, we cannot remove those parentheses with a dollar. I know people have tried, but no, we can't, sadly. So for the R is almost the same. In the case where the list is empty, we just return the accumulator. And when we have a non-empty list, well, we know in the case of for the R, we're going to pass the accumulator untouched until the end of the list, because we are accumulating on the way back. The accumulator is first combined with the last element, which means our recursive call to for R is going to be with the same function f, with the same a, on the rest of the list xs. This is going to give us an a value, which is the accumulator on the way back. And how do we combine x, the element we have here, with the accumulator on the way back? We simply use the f function that we have, which takes first the x and then the a on the way back. And yes, in this case, we can use dollar. Let me check. I didn't say anything wrong here. I can use that also double check that my map as a fold works. Compiles at least. Ooh, it works. I made map with fold on the first try and I have no idea how I did that.
Possibly due to the syntax of the lambda function.
Oh, of course. So lambda is introduced by a backslash because backslash kind of looks like a lambda, and I'm sorry, it's the actual reason. And then you list the arguments, here a and z, then an arrow, and then the expression of the lambda. So here, our accumulation function on the way back, because it's a for the r, right to left, is to say, well, if we have a value a in this list of a's and an accumulator z, which is our result list, because the result of the fold is the type of the accumulator, we transform the a into a b and we accumulate it. We append it at the beginning of the accumulator. But this fold version of map is clearly not what I was asking you to do here. Okay, so I was suggesting at the end of section 3 to go back to section 2 and re-implement some of them using fold. I'm not going to do length because it requires a lambda, and so the most interesting ones. I want to showcase and, or, and concatenation as folds. Because the point of fold is we've spent all the code lab so far doing pattern matching on lists and doing what do we have when the list is empty? What kind of recursion do we do when the list is not empty? And that is 90% of the time, fold, R, and L cover those cases. So instead of writing those recursions ourselves, we can just use fold. And let me show you how that works. So if we want to rewrite end as an endf function, which does the same thing using a fold. Let's say we use a fold L, because that's when that's the behavior we've been doing here by going left to right in the list. We need a combination function. We need a way to combine our accumulator, which is going to be Boolean, because that's the result of our function, with a Boolean of the list. What's the function that we need for end to combine two Booleans? Absolutely. We need a default accumulator for when the list is empty. This is going to be, and on which list do we operate? L. And we've just written that whole thing as a fold. Most of the time, when you're doing a reduce on a list, you don't need to write recursion yourself. That's the point of fold. How do you combine the accumulator and the value? What's your default value when the list is empty? And there you have it. The question I was asked before is, if you look at the type of endf, let me write it in the comments to make it more explicit. So endf, the type of this thing we've been writing, takes a list of booleans. I'm going to write capital B because it's faster, and returns one boolean. Thing is, we don't need to write, in this case, the name L, which is the list on which we operate. This works perfectly as well. Why? Because it's a partially applied fold L. Let me show you what I mean. In this case, the type of fold L is a function that combines two booleans. This is the reason why I'm using only capital B, because I have a lot to type. The default boolean to use when the list is empty, the list of booleans, and returns a B at the end. If we partially apply this with end, we have given the first argument. So the type of this is going to be function that takes one boolean, the list of booleans, returns a boolean. If we partially apply the second argument, which is going to be the default value when the list is empty, true. Oops, one too many. Then the type of this becomes functions from list of Boolean values to Boolean value, which is also the type of endf, which means I can just say this function endf is the partially applied fold L with and true. I don't need to name the list on which it operates. In most cases, I would recommend naming the arguments, because in most cases, having explicitly named arguments is better because you know what you're talking about. In the case of lists, yeah, I think this is okay. This style of writing functions by just combining other functions without naming the arguments is called point-free style, despite it's using often the dot operator, because we don't name the points of data on which we operate. It's a controversial topic. Sometimes it makes things easier to read. Most of the time it doesn't. But it's very fun to play with, and I encourage you to play with it. So same thing for OR. I have only 8 minutes, so I'm going to speed up. How do we write OR as a fold? Well, it's a fold L, because we've been going through the list left to right. What's the combination function for our accumulator? It's the OR operator. What's our base case when the list is empty? It's false. Simple, we have written OR as a fold. Again, every simple recursion through a list and the base case when the list is empty is a fold. Even concatenation. Let's write it as being plus by plus because I can. So what's L1 by plus L2? Well, in this case, we're going to want to fold R, right? Because we are going right to left through the L1 list. What's the coordination function? How do we combine an element of L1 with our accumulator, which is the list we're constructing? Nope, that's not our combination function. That would be the recursive call, which we're not going to do here. How do we combine a value of L1 with our accumulator, which is a list? Absolutely. The way we combine on the way back of our recursion here is by appending the value to the accumulator using the colon thing. So the colon constructor is the function we give to fold R. What's the base case of the recursion? What do we do when L1 is empty? We just return L2. What's the list on which we do the recursion? It's L1. That one is slightly more tricky, but my point here is to say, again, whenever you have to do a reduce on a list, most of the time, 90% of the time, actually, fold is enough for you. So the question of which one should you use between fold L, fold R, fold L prime. Oops, I'm doing.
Question.
Yeah, sure. Oh, it's just I can create my own operators, and since plus plus already exists, I just create that and name that one by plus because I can. I could name it by plus plus dollar something if I wanted. That would be horrible, but I could. Remember the curse. What else did I wanted to say about this? There was something else I wanted to say about this. Yes, there is a very good page on the Haskell wiki about the difference between the different folds and which one you want to use in which case. I mean, one goes left to right, the other goes right to left. So if that matters for you, then that is an important thing to take into account. But for the R, works on infinite list, because it only happens the value, you can read the values without evaluating the whole thing, while for the L is tail code optimizable and usually better for performance reasons. So whether you want to deal with infinite constructs or you want performance, also informs your choice between for the R and for the L. Again, the Haskell wiki has a very good page on this. So section 4 was about maybe. That fascinating type I've been talking about, and I'm gonna see more of it tomorrow. So basically, maybe, as you remember, is a generic type that has two constructors, nothing, which does not wrap a value, and just that does wrap a value. We can use it to implement safe head, because head, again, is partial, crashes an empty list, which is terrible. Safe head is a safe function that just does not crash on an empty list. It already exists. There's a module named safe that redefines safe versions of some of the partial preload functions, but here we re-implement it. What do we return for head of an empty list? Well, there's no value we can return. So the only thing we can return is nothing. In the case where we have some X, then yes, we can wrap it. We can return something. And we can just return just X. Make sense? That's the two constructors to our maybe value. That's the two different ways we create something, when we have nothing to wrap, when we have something to wrap. Okay, so how do we deal with maybes? Well, just like with anything else, pattern matching. So how do we write is nothing? Same thing. Some people have tried to say, well, maybe is nothing of maybe A, we can do MA equals nothing. And same thing, it doesn't work, because for maybe A to have equality, it needs A itself to have the equality, which is not guaranteed here. So what we need to do is pattern matching. Is nothing of nothing is, of course, true. And is nothing, what else could it be? Well, it could be the just constructor applied on some element X, in which case, of course, it's false. We don't need to name the X because we don't use it. And we don't even need to name the whole thing because, of course, if it's not a thing, then we don't care. Yes? Okay, perfect. Yeah, I go through the steps because for some people, it's better clear to see the whole reasoning before you go into underscore directly. So from maybe is the way we get out. We want to take the value out of it, but since they might not be a value, we need to provide the default to be used in the case we have nothing. Literally nothing. So we can do, if we have some default value and nothing, well, simply we return the default value, which is of type A, which is what our function returns. From maybe, if we have just something, sorry, I can't type. If we have just some X, we do not care about the default value because we will not use it. The only thing that matters is X. That's the thing we want to get out of the from maybe. And maybe is almost the same, except sometimes extracting something and then applying a function on the thing makes no sense because applying the function on the default value of your maybe makes no sense. Sometimes you want to apply a function on the things and the maybe and just get the default value for the result of the function instead of extracting first and then applying a function. Because sometimes it makes no sense to apply the function on a default value. For instance, if you have a maybe of a list and you're trying to do something with head, for instance, you don't want to have the from maybe with an empty list and then apply head to it because that would be absurd and that kind of stuff. So how do we write this? Well, we have two things. In the case where we have nothing, we want to create a value of type B. We cannot use the function from A to B because we have no A value. But we have a B value, which is our default. We can use that one. In the case where we have, okay, spoil, we have just some A, then we don't need the default value. We can just apply the transformation function that goes from A to B on the A value to get our B value.